So welcome to the 7th lecture on random processes. We have been discussing the distribution and density functions, right, before this. So what did we discuss among those? Last time I think we were discussing mainly the continuous case, yes, right? So starting from again this guy with t in t and this being continuous, discrete or continuous, and this being discrete or continuous, and then this being finite or countably infinite, and this being uncountably infinite, which is the true continuous case. Yeah, and without going into this part, we were focusing on a single random variable. Yeah, and there we saw that in the discrete case we were defining probabilities at points and probabilities in ranges. Yeah, for the point we had probability mass function or probability distribution function, and for the interval case we had the cumulative distribution function. Yeah, here we had probability density function, right? So this was our probability density function, and the cumulative in terms of probability had the same definition because it's already over a range. But when you try to rewrite it in terms of these guys, then in discrete it turns out to be a summation of the mass function, whereas here it turns out to be an integration of the density function. And again, as I've mentioned already in our discussions, there are two ways of looking at fxx, this thing. It is definitely, whereas pxx has probability, this is p, big P, yeah, the measure probability, yeah, of x equals small x, yeah. Fxx in case of this is not saying this. Yeah. So what is it saying? We've discussed this last time also. This is a relative likelihood. Yeah. And why do we need it? It's a proxy for the PMF for continuous case. Right? And what do we mean by it's being a relative likelihood? Again, it is mainly, you could look at it like this. Uniform distribution is a good example to start with. So we looked at this last time. Quick review here. If this is 0 to 1, then this is a uniform distribution, and this has to be 1. Total area will be 1. The PDF now, let's say fx at 0.5 equals 1. Is it saying probability x equals 0.5 equals 1? And let's say fx 0.6 also equals 1. Is it saying probability x equals 0.6 equals 1? No. Yeah. Then what is it saying? One way of looking at it is to say it's the relative likelihood. It's saying both are equally probable. Yeah. And then we have this spread their probabilities in a way that they meet certain criteria. What are those? Basically, one of the most important one cannot be negative. Total area has to be 1. Yeah, right. So, and the other way mathematically you want to look at it, this one, if you want to write it in terms of equal to probability. So far we haven't been writing it like that. Yeah, if you want to write it like that, there is one way, other way of writing it. It's the rate of change of the cumulative distribution function. Yeah, it's the rate of change of that function if the derivative exists. Whereas still in all of these we are still not able to write p, capital P on the right hand side. Yeah, So still, okay, what does the rate of change of our cumulative mean? Still not connecting to probability. The only way, the only way I can think of right now to connect this to P as equal, to say, okay, what is the probability of finding X in an infinitesimally small interval, X plus dx, yeah? This is mathematically sound. So again, rate of change of the cumulative, you could call it that, but doesn't really give you much other than mathematical juggling. This conceptually, yes, makes sense. Relative likelihood, yeah, and here also it makes sense. Yeah, it's the probability of that. In this form, it is again not point, it's an interval. So the only thing is interval is infinitesimally small. Yeah, okay. So this was a very quick review of I think last 2 or 3 lectures, but what's next for us? Yeah, so far we have been talking about only one random variable. Yeah, we have talked about more than one random events before, probability A and B, but there we weren't really formally defining them as variables. We're just saying event, something happens A, something, then another thing happens B. Yeah, those were events. Since now we have gone into variables and we have looked at a single random variables, all the details, I think we have set the foundations of what we need to do to get to random processes. Yeah, but random processes, there is one step in between. Okay, that is making the jump from 1 to 2 random variable. Yeah, so let's cover that also. Then jumping from 2 to n will be simpler. Okay, so let's today mostly we will be going from one random variable to 2 random variables. Yeah, not another, I mean looking at functions, behaviors of one random variable to looking at 2 of them. Yeah, 2 random variables, and then towards the end, if there is time, we will go from 2 to many. Yeah, like in Arabic, you know, they have this, we don't have in Urdu or English. In the Arabic grammar, they have things for 1, right, then 2, and then for more than 2. Most other languages I know at least have 1 or more than. Right? So in Arabic, there is this difference. So same like that, we will go from 1 to 2 and then 2 to many here. Okay, so let's write the theme of the lecture today, from 1 RV to 2 random variables. And we will follow the development that we did for a single variable in terms of now 2 random variables, and we will see what kind of density and distribution functions replace the single variable case. You know them basically, yeah, joint and those. But let's develop this more formally to see. Now, remember we defined a random variable over some random event. We mapped. We said the mapping wasn't unique. There were many ways of mapping. Yeah. So let's start with that and say, okay, maybe we want to define 2 random variables over a sample space omega. So there is a sample space omega. Let's say rolling a die. Yes, and we want to define 2 random variables on it, x and y. So I say for me omega is number on the die that shows up, yeah, when you throw it. And I say I want one random variable x omega to be omega. Yeah, so what are the possible values of x?
1, 2, 3, 4, 5, 6.
And I want another random variable y omega to be omega square. That's it. I'm not saying we are limited here, right? There's a lot you can do. Just want to show some examples. So this is one mapping you could do, right? Okay. So you know what are the values of y omega then? Yeah, squares of whatever x omega would get. There's another mapping we could do, just like we saw for the single case. So I will go through it faster because we've discussed it in detail. Again, omega is the same, is the number on the die that shows up, and I say x omega is omega and y omega is 0 if omega is even, is 1 if omega is odd. Now what are the possible values?
The first is
1, 2, 3, 4, 5, 6 here.
0, 1, 0.
Yeah, so it will be 0, 1, 0, 1, 0, 1. Yeah, for the even numbers 0 it takes. So it has only 2 states. Yeah, and you can guess the probability of each state, 50%. Half of the numbers are even, half of the numbers on the die are odd. Okay, so now when in algebra, when you go from one variable to two, first you have x equals 7, let's say, okay, some variable that fixed this value, but then you also bring in another variable x and y. Yeah, so what are some of the earliest things you look at when you study algebra in, say, university? It's their relation, isn't it? Are they equal? What does equality mean? Yeah, is less or equal, less, greater or equal, greater, whatever. Yeah, so you automatically, this thing wasn't there in a single variable. As soon as you go from 1 to 2, interrelations start showing up.
Summation, subtraction.
Yeah, their operations start showing up. So same will happen here. Now we've gone from 1 to 2, so their interrelations will start showing up. So just to jog your minds a bit, when can we say that, let's say we have done one of these mappings, whatever, or let's say we don't talk about the mappings exactly here. Let's say these are x and y are defined over omega sigma field, remember? So this write it like this, and the probability measure. Measure theory writes things like that generally. So measure theory आपने की है किसी और course में? No? When you did graph theory, you didn't come across any? No. Right, so x equals y. Two random variables defined on this thing. When are they equal? So we want to get this out of the way first. What do you think? When can they be equal?
When the mapping is same for both, then they will be equal.
And the mapping is? Same, yeah. So, and if we don't want to go into mapping, we could look at their values. We could say, okay, if x omega equals y omega for all omega, right? So this is more in terms of sets. Yeah. So for every possible omega, remember they were defined over this already. Yeah. So for every possible omega, the two take the same value. Then we say that they are equal. Yeah. This is the equality of two random variables. Yeah. Okay. Now these are, there is something, these are surely equal. I don't have to write surely. Okay, they are equal. Yeah. But there is something called almost surely equal. Okay. Now, have you ever come across this term almost surely in any probability, stochastic processing course?
Almost everywhere.
Almost everywhere, yes. Measure theory, it's the equivalent of that, yes. Yeah. In sets, you have sets are almost equal. When are two sets almost equal?
if they are equal for infinite many videos but not equal for finite videos.
Yes, exactly. So I will describe this, yeah.
Yes.
But this same thing for probability, it turns out to be in terms of surely, almost surely. Because remember, sure, certainty, uncertainty. This is what we are dealing with. When you were doing that one, that was almost everywhere. Not talking about surely, unsurely, because they weren't dealing with probability theory. Similarly for sets. First, let's start with sets. So two sets are almost same or equal. Let's say you have a set of natural numbers, okay, and then I define my own set. Yeah, I'll call it just S, which is set of natural numbers minus just remove from it just 1 point. Let's say I don't allow one. I don't like it or something. Yeah. So are S and N equal?
Not equal.
Not equal. Yeah. Yes. Two sets are, when are they equal? When they have same cardinality, same number of elements, and each element are one to one are the same. Yeah. Now here the issue is they are not equal that we can see almost. Yeah. But notice they are equal in infinite number of places. N is infinitely large. Yeah. So they are equal in infinite number of places, but unequal in only one place. Yeah. So in from set theory you call that almost equal. Similar thing will happen for us in probability theory, where we will sometimes talk about an event happening almost surely, or sometimes we write it with probability 1. And then you will say, hang on, if you are saying this will happen with probability 1, what is the difference between this and saying that this will definitely happen? There is a difference. This you will see that there will be an infinite number of ways that event can happen, and only a finite number of ways that it does not happen. Then we say it's almost surely. But if you take away even those finite number of ways that it cannot happen, then it becomes surely. Yeah. So we will come to that later. For now, I'll start with two random variables being equal. Sure, this is surely equal. When we just say equal, what are we talking about? Surely equal. Okay. But when we want to emphasize that they're not really equal, then we will bring in almost surely equal. So when are two sets almost surely equal? Well, usually this kind of things occur in the continuous case, and I will write it here. Let me write it with an example. So I've already mentioned it here. If let's say if there is an infinite number of omegas where they are equal, and only finite, maybe 1, 2 or whatever, finite number of omegas where they are not equal, then we will say they are almost surely equal. So let's write this one as an example. Say let omega be in the set of real numbers. Yeah. Then we will say okay, so our this omega is now capital omega is r. Then we'll say x omega equals, if we have this, then if we have x omega equals omega for all omega in r, then are they surely equal or almost surely?
They are
Surely equal. Yeah, there is no exceptions, even finite exception. There is zero exception. So these are surely equal or equal. We don't need to write anything here. This is the equal thing. Yeah. What happens if what's going to happen if I say okay, x omega equals y omega for all omega in R except omega equals 0.5. Yeah. So the set now omega is where these are equal is r minus 0.5. You remove 0.5 from this set. So there are infinite values where they are still equal. Yeah, there is a finite value where they are unequal. Yeah. Now that thing we will say x is almost surely equal to y. We write it a s. Yeah. Another way people in probability theory write it is to say that x here x equals y. Here x equals y. Here there is another way of writing it is to say x equals y with probability 1. That's another way of writing almost surely. When you skip this or this, you are talking about x is actually equal to y. If the other situation holds, then either you write it like both are used in literature of probability theory. You say, and we will come back to this in distributions. We'll see when distributions are almost surely equal. Okay, so that's why I want to cover this a bit now. When after this, whenever I say almost surely equal, you have a mental image of what it could mean. You have idea from measure theory already, but even if you don't, as I've explained, this is what's going on. Okay, so x equals y with probability 1. Why do we say this makes sense almost surely? Yeah, almost. But why do we say with probability 1?
Probability kind of an uncertainty.
Yeah.
There is a little bit of uncertainty. Then probability 1, it makes sense that it's approaching to 1. So
It is approaching. So it's a very interesting thing for the continuous case. This is continuous case. Yes, they are unequal only at one point. Yes. So if they are unequal only at one point, then what is the probability? Because let's just write it here. Probability of coming to an omega, getting an omega, yeah, where they are unequal is zero because there's an infinite ways that there's infinite of these guys. Yeah, what are the chances among those infinite ones you will find this? Let's say for this case, what are the chances from probability theory point of view that you will find exactly that one point where they are unequal? Yeah, it's actually from this is again, it comes down to the same issue. Remember I said when we looked at continuous case that the probability of any given point is 0. You could say approaches 0, but for all practical it is 0. Yeah. So what is the probability that you will come across an omega where they were unequal? So I know they are unequal. Now in the truly equal case, this will never happen anyway. Yeah, because they are equal on all. But in the almost surely case, I'm explaining what the equal with probability 1 means. Then can I say that probability of finding omegas where they are equal is actually 1? Yeah, it's a kind of a little bit counterintuitive effect of the continuous case. Yeah, this is the sentence that is here. Okay, they are equal with probability 1. Okay, so if you don't need to write that, then it means there isn't even any omega that does not exist where they were not equal. They were always equal from the start at every omega. Then you don't need to write these qualifiers. Yeah, almost surely, with probability 1, and so on. Now this is so sometimes we summarize this as prob. So in some books you will see it saying prob 1. Okay, they are talking about almost surely case. If they were actually equal, they will not have to write this. Okay. Now same thing can be for almost surely or prob 1. less or equal to y greater or yeah, all these things can happen. Yeah, so I will not go into that thing. And you can I have some more examples here, but I think we can skip. You get the idea of surely and almost surely. We will leave it here. It will come back at some point in if I recall correctly, it will come in distributions, but I'm trying to recall is it which distributions. Anyway, we will come to that, and we will see when is a distribution almost surely normal. Yeah, almost surely this. Yeah, so it's a very useful practical thing, right? So with this out of the way, yeah, mapping, defining, then a little bit of their interplay we have discussed. Now we are ready to talk about the distribution functions for two variables. Yeah, so which one? We have discussed the probability of two events, we have discussed, right? What were those? How many ways did we discuss that? So if there were two events A and B, you could have probability of A, probability of B. You could have probability of A and B, probability of A
Union.
or B. Yeah.
Additional probability.
Then you had probability of A given B or B given A. Yeah. Then there is the complement, but it's S minus. So yeah. So there we had done this. That's fine. But now we want to go to variable. So what's the function? What functions come to mind? There are several. Yeah. For the cumulative distribution, what do we get? Joint cumulative distribution. Yes. So in this case, there is a special name because these are two variables. It's called bivariate cumulative, which is a special case of the joint, which will be for any number of variables. Yeah. Joint of course covers bivariate and univariate. Yeah. But now let's look at the bivariate. Then it will be easy to extend it to multiple random variables. So can you help me define this thing? Fx, y, x comma y. So now two random variables. Yes. Equals क्या होगा? This is still a cumulative, remember? So from the single variable cumulative, you know that one. It was for an interval. Yeah. So अभी क्या होगा?
Probability of x less than
Double integration.
नहीं, probability of x less than or equal to small.
वो तो जब when you try to write it in terms of PDF or PMF, then it will come. Yeah. Or in terms of probability itself, how do you write it?
Minus infinity less than equals to x.
So x is less or equal to x. If we don't write, we will minus infinity. Yeah. And y is
less
Less
than
than or equals to.
y. This is like probability of A and B.
Yes.
Yeah. What are the A? Event A is that x happens to be less or equal to, and meaning it lies in the interval minus infinity to x. Now for a single case, the interval used to go like this. Yeah. For the double case, the interval now has become what? Infinity to x and minus infinity to some y. So now it has become a region instead of an interval. And where is this guy? The third dimension. Yeah. Z axis पे आ गया ना. So after that you cannot imagine. वो फिर mathematically you can do for three variables, but you know it goes into 4 dimensions. You cannot imagine, but you know how it is. So where is this guy now? It's in here. What is the value? Like if I could draw, if you could imagine this coming out of the board, then the distribution values, all of these are assigned some value. This is coming out of the board where it's high. Yeah, that is so. Right. So Of course, now we try to go to the bivariate mass function, discrete case. Yeah. So this is bivariate cumulative distribution. Then we go to bivariate mass function. Yeah. So what could that be? P x y x comma y equals, of course, in terms of probability it will be
X is equal to y is equal to.
yes, but then we try to relate them that you were mentioning. So what is fxy, not in terms of the p, the probability, but in terms of the mass function. What would it be?
Summation in discrete case summation. Summation x start from
Summation x plus summation
X
y.
I y I
And
summation y
y I less than or equal to y.
and then where is that? Yeah.
Probability of
x.
x and y.
Right. So whereas in case of single variable, you were summing these like this. Now you have to sum over all the points in the region, this region. Yeah. So good. What about the continuous case now? In continuous case, as before, this is already an interval, so we don't need to change it. But this thing has to be replaced by its proxy, the bivariate density function. Yeah.
Partial derivative.
Good. इसलिए पढ़ाते हैं आप. Yeah. So what is it? F x y x comma y is
Partial derivative with respect to x.
not. I won't be able to write this. Yeah. सही है. Clear है ना? We cannot write this for this guy. It has to be in other terms. So what is it? Partial
Partial x, partial y.
yeah. So the other way by then what is fxy in terms of this
Integration minus infinity to x.
Integration minus infinity to x.
minus infinity to x and minus infinity to y. Dx dy or dy dx on here. Yes. Simple. So now what is before the single one was represented area under this guy, and now it's representing the volume. Yeah, remember? So now this thing, even the density function is defined over some region of x and y. Then the actual function now has to go into another dimension. It will be up here. So the volume under that will be your, depending on what. So let's say you want to minus infinity or let's say you want to do from 1 to 2 and 1 to 2, then you're talking about 1 to 2 and 1 to 2. You pick this region, and whatever volume falls is covered by this. That will be the joint probability of
Joint
X.
cumulative.
yeah, the joint cumulative. Yeah. So you get the idea. Again, I'm going through this a bit faster. We spend a lot of time on even this thing, showing students in undergrads with the help of a table. We take discrete case of say rolling 2 dice or something, and we show them the value. Then we sum it up in but in your case, I can skip that. It's a graduate course, so you can start imagining what's going on here. Yeah. Okay. So let's see what next. Yeah, when we went to two events, yes, I mentioned probability A and B, A given B, and that's okay. there was one more important concept that we discussed, right? What was that when there were two variables? It was related to conditional probability. Bayes theorem is like, yeah, it's a result of something, but independence. Remember? So we discussed, okay, when are A and B independent? Two events, yeah? So what were the conclusions?
In that case,
So it was, there are two ways of showing it. Probability A given B equals probability A. We discussed it in detail. All it's saying is that the knowledge of B does not change the likelihood of A in any way, then that knowledge is useless. So in that sense, this is independent of A. We also found that we could also write it like this. They are equivalent, yeah, because of the definition of the intersection thing. So, or sorry, this probability A given B is probability A intersection B divided by probability B. From there you can always come to this point. So this was also another way of showing that A and B are independent. What does it mean mathematically? That their joint probability is separable. Yeah. If it's not separable, then they are dependent. Now the same thing can be translated in case of distributions for random variables. I didn't talk about that in the single variable case because it doesn't make sense. It's one variable. You need at least two to talk about equal, almost surely equal, equally probable, all that. Yeah. So let's see. So yeah, we will say from here on that two random variables are independent if they are joint or bivariate cumulative distribution function is separable. That is, their joint one is actually a simple product of their individual cumulatives. Yes, then they are, this was independent. All of these represent the case. This was for events, this is for two random variables. It's not limited to here. There is you can also test this from fxy, x comma y being separable. All of them are equivalent. Same thing you can do with the mass function, yeah, for the discrete case. So I won't write it, but you get the idea. You can see Kobayashi chapter 3. If you want to go into the derivations of these, but here I want to connect the concept to what you have already covered. Actually, if you start here and remember what these definitions were in terms of probabilities, you can easily get here. It's not a big issue, but still you can go through here. Right. So the bivariate cumulative will also have some properties like the single one had, univariate had. So can you think of some properties this guy will have?
It's always be a non-decreasing.
Okay, let's see. What else comes to mind? It's the, yeah, non-decreasing is fine. What else? So f x y, of course, it has to be. Can it be negative?
No, greater than or equal to 0. No.
Okay. What else?
Equal 1.
Total volume 1 over 1.
Yes. And the way of writing the total volume thing is
Infinity to infinity.
yeah, 1. Mathematically it's the total volume, yeah, but conceptually what are we saying? That x and y lie in the range minus infinity to infinity. Of course they will. Yeah. Or कहाँ जाना? We covered everything, yeah. So it will be, because we are saying x lies between minus infinity to infinity, y lies between. We're giving them everything, yeah. So it has to be 1. This one is interesting. Let's see if you can guess. First tell me what it means, then we will write something. What is this? You understand, yeah? What does this mean? In words, like no formula.
That is kind of a plane, a cuboid type planes are इस किस्म की चीज़ अगर हम कहें ये बन जाएंगे जैसे ग्राफ के लिए ड्रॉ करें तो x को हम फिक्स रखेंगे y को infinity पे ले kind of a cuboid that will get.
Okay, but what does it really mean? Represent, like here I told you like x and y can take any value, right? So that was 1. What does it mean in words? You're thinking in graphs, so we will come to that, yeah, but it's always best to start with words.
X takes value from minus infinity to x. Y takes value from minus infinity to infinity.
So what? Okay, that is fine. What should be a natural consequence of that? Are we saying what are the chances that y takes the value from minus infinity to infinity? We are saying y can be in minus infinity to infinity. What are the chances of that? We'll take 1. And so it's irrelevant, right? We're allowing it all values, so it becomes irrelevant. When y becomes irrelevant, so what should this be then?
F of x.
F of x. Right? You're saying y's value is like, yeah, it's all of it, yeah. So if you imagine it like this, it's x minus infinity to x and y minus infinity to infinity, right? So basically you are from minus infinity to x is fine, but then you're allowing all values of y, so y will not contribute anything to this distribution, yeah. So this becomes fx x. How can I make fy y? Fxy equals fy y when
infinity and y comma 1.
Yes. So this is the reverse of that. Yeah. Here you are saying y can take, x can take any value, which of course it will. So there is nothing to add there. Yeah. What is the name given to this kind of calculation? This, of course, this is the distribution of this is the cumulative for the individual case, yeah. But when you derive it from the joint, we have a name for it. It doesn't change, it is the original one, whatever it was supposed, but because we took it out from here, we give it a name. याद करें और कौन सी याद? Joint distribution function, probability density function, cumulative density function. What else? Huh? Starts with an M.
Mutually exclusive. Mutually exclusive.
No. There's A here, then an R.
Marginal.
Marginal distribution. Yeah. Now marginal distribution is not different from the univariate. This is the univariate. Why do we have this new thing here? We could just call it the univariate. It's just the emphasizes the fact that the way you obtained it was from, you extracted it, and it's not the only way to get it out from here. Yeah, there are other ways, but whenever you do that, we will call it a marginal distribution. But sometimes in undergrad, students think this is something new. This is the original univariate. Yeah. But because we derived it in a certain way, we call it the marginal. So what about the marginals of, let's say, I wanted to get marginal from, this was the marginal cumulative, yeah? What about marginal density? Can I get it? So I have fxy, yeah. So let's leave it here for you, and I want to extract from it the individual distribution of x, which we will now call the marginal density. Yeah, this is the PDF. So क्या करना पड़ेगा?
Integrate करना पड़ेगा with respect to y.
With respect to y. So are you sure?
Respect to y करेंगे then फिर x आएगा ना हमारे पास.
फिर आपके पास
y तो खत्म हो जाएगा.
So what is the range of
minus
y?
infinity to y.
Minus infinity to y. Sure.
minus infinity to x और minus infinity to infinity y की होगी.
तो वो तो हम हटा देंगे ना. Yeah, so this will leave you here with, because minus infinity to x, you cannot use x here, so let me check.
सर ये
No, I think you're right.
minus infinity.
Yeah, so we have to integrate over y.
y.
So minus infinity to infinity, and we will let x be here. This will be nu and d. So we take all possible values of y into consideration, and what it leaves is fx x. So you know which rule you have used here in a way? We studied that after Bayes' theorem. The law of total probability. Yeah. So one variable takes all its possible values, right? Then with those, the original one, the x, you can extract here. So similarly for getting fyy would be
y.
so it will be f y y. So what are we really saying? So remember this guy. So this is around x, this is y, and let's say they are over some range. Yeah, and then your this function is in the third dimension, right? Now when you are integrating it over, let's say, the whole of y, like here, yeah, so you are allowing whatever range of y had. In this case it's from here to, let's say, alpha. This is from 0 to beta. So the total integration of course has to be 1, which will be the total volume under it. But when you are integrating from minus infinity or in the whole range of y, which in this case is 0 to alpha, yeah, so what volume are you picking up from here? The value of x, yeah, let's say it's 0.5, 0.1, just imagine that particular value. Then what you are doing is basically you are here, yeah, so you are taking this, the volume that falls on this region, small region, yeah. So essentially you are collecting the value that you should have for a particular case of x, yeah. So it's like, what is the probability that x takes 0.5 and y takes, let's say, this value. What is the probability that x takes 0.5 and y takes this value? What is if you sum them all up, continuous sum, like integral, or in this case, yeah, basically the integral, then this is like what we did for total probability. Remember that case where we saw what's the probability that you win, that you play team A and you win, plus probability that you play team B and you win. So as long as we covered all the possibilities of the B event and summed it up, we got the probability of the event A alone. Yeah, this is very similar to that thing happening here. Okay, so just try it out little bit and you will see. So I've already mentioned that the total area under these has to be 1, so for completion's sake I will write it. Minus infinity to infinity and minus infinity to infinity, fxy xy dx dy has to be 1. Same thing for the summation. Yeah. Right, so how much time? Okay, we still have time, so it's my last sheet. Here in one simple page we go from 2 to many. Okay, whatever we have discussed, it becomes rather simple. So I'll just write it out first and then we can discuss it. Not a big jump. So now two to many. Yeah.
Yes.
So we could have directly gone to this, but we would have missed some important revisions there. Yeah, inside of joint and all that. So let x1, x2, x3, xn or m be m random variables defined on some sample space omega. Then we may define a multivariate m dimensional joint distribution. Okay, so now we call it univariate, bivariate, multivariate. Yeah, multivariate joint distribution, and I will write it as vector x. Okay, so for our convenience, x is x m. Yeah, so vector like that. Could be a row vector, doesn't matter. But here x1, x2. Notice these are capital, these are small. Yeah. So can anybody help me write in terms of probability?
Probability x less than x1 less than or equals x yes x1 then less
And yeah,
x is less than or equals to x2 xn is less than or equals to xm.
yeah, no big deal. And the mass function and the density function may be extended similarly. Okay, I don't have to write that. It will, what partial derivative will be mth partial derivative of this guy, and if you want to go from here to here, then it will be how many integrals? M integrals, yes. And also you can extract different marginals from it. So I'm not going to write that, it takes a lot of space, but the benefit of going from 1 to 2 is that I don't have to do all of this. You can imagine a natural extension. Yeah. Okay. So the only thing that needs to be discussed mainly lastly is independence of many random variables. We never talked about we said probability when A and B are independent. We never say are A, B and C independent. How do you do that? Yeah, so for A and B it was easy, yeah. But now I want to say A, B, C are independent, meaning they are all independent of each other. A, B are independent.
Given B intersection C or something.
Yeah. Essentially, each of them will have to satisfy. Each pair will have to satisfy this. We didn't cover that, but similar here we can try to see. Okay, when are more than two events independent of each other? Similarly, when are more than two random variables independent of each other? So, any guess what we did for two case? What was it in terms of, let's say, x, y? We said they were independent if they're
product of their marginals.
yes, product of their marginals, meaning they were separable. Yeah, so it was like this. If you extend this, what should you get for the multivariate case?
Product for M marginal.
Yes, so it should be a product of M marginals. So just to make it, let's say I have x, y and up to some z, and I have xk. I will mention why I have gone from this to this. I just want to make something clear, that's why I have written it like this. It has to be a separable product of their individual distributions, which is xk, fx, yl up to fy, fz, zm. Now here, maybe I forgot to mention something, but whereas in events, probability of A intersection B equals probability of A times B, they are separable, they are independent. Okay, here it's not. Notice it's not one value. Yeah, this has to hold for all x, y. Maybe I forgot to mention that, but from the general, it's not enough to show them separable at 0.5 and 0.6. No, they have to be separable for all selection of x and y. Same thing will happen here. Okay, so this thing has to hold for all xk, for all yl, and for all z, whatever they were, yeah, zm. So just to emphasize this thing, I've shifted, because otherwise I'll have to use double subscripts. So I shifted to that. Now, based on this, you can also rewrite for the probability mass function. Remember, for two variables they had to be separable. Probability density function had to be separable. So you can imagine something similar for this thing. Yeah. So with that we have basically covered what I say lecture 3 here. Took 3 lectures, but I think when I was writing this I wasn't thinking of our 1 and how much do we have? An hour and 15 minutes. Yeah. So what's next then? Where are we now? We started with uncertainty, lack of knowledge, probability, events, independence, base, right? Total probability. We jumped to going from deterministic to random in terms of events, variables, processes. And then we zoomed into one random variable and we split it into discrete continuous. Then we zoomed out and went to 2 random variables, yeah, and their distributions and all that. What's next?
Special random variables types of random.
Yeah, there are many things that can come next actually, but in a standard course usually.
Expectations, variance.
Yes. The
Deviations.
yeah, expectations, the moments mainly.
Moments, yes.
They are usually after distributions. We haven't discussed the actual distribution. We will come to that, Gaussian and all that. But we have set the functions that we will use. cumulative, bivariate, univariate, joint, marginal. We have established all of that. Yeah, but we didn't go into any particular ones. We gave example of uniform, but that will come later. For now, we have established the general group of functions that represent our distributions. What are their cases? Gaussian, Poisson, so many others. We will come to that later. But before that, I want to stop at the moments. Okay? Because once we have that and this, then we can go to special cases. Okay, uniform, what are the moments of uniform? What is, okay, Gaussian, what are the moments of Gaussian? But before we talk about that, we should have a very clear idea of what are moments really. What are the moments useful for a single variable? What are the moments useful for two variables? What are moments useful for more than two variables? Yeah, multivariate cases. So before we will do that next time, but I want to give you an idea of this. As we will find from an applied point of view, dealing with full distributions, especially when there are multiple variables, becomes a headache. They become very large functions. Okay. The practical way people have done is to extract some useful information from the distribution. That I again call the proxy, or the value that represents some important parts of the distribution which we can use in our decision making, in our estimation, in our design. Yeah, that information that you extract out of these guys, because they are going to get very ugly. When we will write a joint PDF of Gaussian, you will see, yeah, they will get ugly, and the calculations will get ugly. You could do that, but for most practical purposes, it actually helps to extract some of their key features. Yeah, and one way of doing that is to go towards moments. Moments mean expectation, variance, covariance, right? Higher order moments, kurtosis, skewness, those, they extract some information, and then instead of working with this huge function, all of a sudden you are working with small variables. Yeah, so that makes applications more practical, and there are other basically conceptual uses, but in essence, this is what I want you to keep in mind. It's not, many times students go through learning these things, but they don't connect them. Okay, there is a connection for practical purposes, and for efficient working, we will extract some useful information from the distribution functions, and those will be the moments. Okay, and we will also see in many cases that moment functions can represent the distributions again. Okay, moment generating function, and you can get the distribution as some sort of weighted combination of moments. Yeah, but that we will do next. So before next lecture, I want you to think about what exactly is the expected value. What does it mean? What exactly is variance? I know you know the formula.
Yes.
Yeah, but I'm going to ask you the concept. Okay, so think about it, and we will cover that in some detail. So that's next. Yeah, we can stop this.